I'd like to talk about related rates problems with you. Related rates problems are common in Calculus 1 in the world of an application of implicit differentiation. And they're almost always word problems, and they involve some sort of time. There's going to be one rate of change related to another, and they're related implicitly through time. And this is a really good example of that type of problem. I'll read it with you. A 5-meter ladder leans against a wall. The bottom is 1.5 meters from the wall at time t equals 0 and is sliding away at 0.8 meters per second. Find the velocity of the top of the ladder at time t equals 1. Okay, so we want to find a velocity of the top of the ladder at t equals 1. The only way we're going to be able to get a hold of this problem and really wrangle it under our control, I think, is by first we got to draw and label a picture. And when we draw and label the picture, the labeling is going to be kind of up to us to name things, and choosing names to match the situation, I think, is pretty important. So let's draw a wall. Here's a wall. Here's the floor. And then let's put the ladder like this. And I know that no matter how far down the ladder goes, the length of the ladder is always 5 meters. Okay? So the length of the ladder is always 5 meters. So there's a ladder like that, and its length is always 5. It says something about the bottom being 1.5 meters from the wall. So that's the distance along here. And then we could like name the height here, and that seems pretty helpful. So we're gonna like name quantities in this diagram with the hope of describing the situation. So I think that we should probably call, this X, and I think that we should call this, say, Y. And that's the distance from here to here, or from there to there, or could perhaps be like that point or that point. Okay. So we drew a picture and we labeled some stuff, and our objective is to state stuff that I know from the problem in terms of the state variables X and Y, as well as their rates of change with respect to time. So I feel like we should try to like say something about X dot or Y dot, or that is to say dx dt and dy dt. And I really like using like arrows in my diagram to help indicate motion. So the ladder's leaning against and it's sliding away. The bottom is sliding away, so it's going down in that action. So this is going there, that's going there, that is going that direction, and that is going in that direction. So we're going to try to label the rates of change of these two state variables with either that's my objective to find it out, or I know it somehow. So from the statement of this problem, I've got that the bottom is sliding away at 0.8 meters per second. That means that this is 0.8 meters per second. This arrow right here represents that this is moving at 0.8, and it's shrinking. So then dy dt. Well, okay, so find the velocity of the top of the ladder. Y represents the position of the ladder. So the velocity of the top of the ladder is moving strictly down because it's pushing away. So I think that our objective then is, dy dt. This is the thing I want. And one of the things that we should really work on when doing one of these problems is identify the thing that you don't know. Okay. So I've got X and Y, 5, dy dt, dx dt, and I want to relate those two things, those things together. Okay. So I happen to know that I have a triangle right here. And furthermore, so 2, I think we should relate. We're going to relate the variables. Okay? And the variables in this case are x and y. So I have a triangle, and so I then know that x squared plus y squared equals 5. But I know that this is also changing with respect to time. So I also know that x of t squared plus y of t squared equals 5. And so I feel like putting that time dependence explicitly in our relationship is really important, at least when we're learning how to do these problems, because it's the thing that hints to me, oh, these are functions of time, and then I want to take a time derivative of these things. And so I think that our third step then is, after I've related the variables, let's take the time derivative, and that's going to use implicit differentiate. So we're going to implicitly differentiate that equation. So let's see here. Okay, so I've got something squared. And anytime I have something squared and I take the derivative of it, I have 2 times that something. And then I need to chain out the derivative of it. And x is a function of time. I'm taking the time derivative. So implicitly differentiating with respect to, WRT is with respect to time, okay? I'm not differentiating with respect to x. I'm not differentiating with respect to y. I'm differentiating with respect to time. Since x depends on time, now I have to chain out the derivative of the inside of the something squared, and I pick up times dx dt. Because of the chain rule, we're going to get something similar on the right-hand side. 2 times y times dx, dy dt. Because y is changing with respect to time, so the chain rule dictates that I have to chain out a time derivative. And on the right-hand side, equals, what's the derivative of any constant? 0. So now I have a relationship that couples together xy, dx dt, dy dt, which is going to be awesome. And to remind ourselves, what's the thing that I want? I want to know that thing. Okay, we know that, okay, so now it's like implicitly differentiate. We've identified our objective, and then we're going to use the things that we know and solve. And I think we should solve for our objective, whatever our objective happens to be. Kind of looks like it goes. Okay, so let's see here. So it's 1.5 meters. The base of the ladder is 1.5 at time t equals 0. So let's use our multi-time diagram on the left-hand side right here. Let's redraw this to indicate what's going on at time t equals 1. Okay, so I started with this situation where that is 1.5. That's 5. And that's at t equals 0. So then at t equals 1, the ladder has slid down. And I need to know what's that distance, because that's going to be the thing that tells me what y is. Okay, so that distance, well, it was 1.5, and 1 second has elapsed from t equals 1, 0 to t equals 1. So how much time elapsed? 1 second. It was moving at 0.8 meters per second, which means that this is 2.3 meters at time t equals 1. So in step 4, I'm solving, and I happen to know that 2 times 2.3 times dx dt is 0.8 plus 2 times, let's see here. Do we know why? I think we do know why, because of our relationship that we started with. Okay, so let's remind ourselves what we have. This right here is x at 1. This right here is dx dt. Then we're going to have y at 1 and our unknown dy dt. So we just need, and that's equals 0. So we just need to figure out what y is at time t equals 1. So let's do a little bit of work up here. Lots of scratch work. These problems almost always take like a full sheet of paper if you're actually leaving yourself room, which is totally something that you should do. Okay, so I know that 5 squared plus 2, nope. Let me try again. I know that 2.3 squared plus y squared equals 5, which means that y squared is equal to 25 minus 2.3 squared, and 2.3 squared is 2.3 squared is 2.3 times 2.3. I think it's 5.29. I think it's 5.29. Yeah, because like 2 times 2 is like 4, and like 2 times 3 is 6, so like 2.3 times 2.3, somewhere around 5. Seems good. Okay, which means that y squared is equal to 25, nope, I already did that, 19.71 with a square root. Oh, that's what y is. Okay, so y is 19.71, which means that over here I have the square root of 19.71, and then my unknown that I want is the quantity dy dt. Okay, and that's our objective. We're going to solve for it. So I'm going to take this expression and move it on to the other side. And I will have that I have 4.6 times 0.8, that's with a minus sign, equals 2 root 19.71 times dy dt. And finally, I'll divide by that on both sides. So I have 2 root 19.71. And that's what dy dt is equal to. Okay. And that was my objective. I found it. Of course, if you really want, you can plug this stuff into your calculator and come up with a number. It's going to be somewhere over, I don't know, somewhere in the order like minus half or something like that. I don't know. I think it's important to note the SAGN sign of this quantity is negative because this is falling, right? Y is going down, and so it should be negative because it's falling. Okay, so let's review the steps that we took. The first thing that we did when we approached this problem was think to ourselves, okay, I need a picture. I need names of things in order to have command over them. So we're going to draw a picture and label everything in the picture with a symbolic quantity. And then we're going to relate those variables together as an optional step. Remind yourself that these are functions of time. And then differentiate this expression with respect to time, remembering to chain out derivatives, time derivatives of things. And finally, identify the thing that we want to solve for. Know that we have these other things. You almost always will have to use this relationship to get another piece of something. It's a very common pattern. And then finally, we're going to take all those pieces and put them together and then solve for whatever we didn't know that the problem is asking us to solve for. In my mind, the most important part of this process is the drawing and labeling of the picture. Without a picture to help me work on what part relates to what part, I think I'm kind of dead in the water. So I think you should always start with the picture when working on a related rates problem and go from there. And it's like draw and label and just make up names for things, just make up symbols. And you can always like throw away the piece of paper and try again later. So hopefully that helps you get a handle on some of these related rates problems. There's like practically infinite number of them. There's some pretty common ones, and then there's like really wild ones out there, and everything in between. So thank you very much for your time, and I will see you again for my next video. Bye.